Hello, everyone, and welcome to a short series on drones and their use in agriculture. I'm Hunter Windsor, a PhD candidate in plant environmental sciences. I've done a lot of work with drones over the last couple of years, and Dr. Edgar asked me to come give you guys a lesson on how to do a bit of precision agriculture interface with drones. So a bit of my own background is that I used to do a bit of archaeology and paleontology work with the Bureau of Land Management in Arizona. And my current research involves digital soil mapping, which involves large computers and really big data sets, but not too much field work. But kind of like my interests lie in the use of kind of novel sensors. So here I got to use the state soil scientists' ground penetration radar, and it was a bunch of fun. But that's also how I got into drones. And so you can attach just about any kind of sensor to a drone. And here's a photo of me in Utah surveying for biocrusts using that M600 drone, which is about a 6-foot wingspan, six rotored, uh, six rotored copter. And the individual biocrusts that we were looking from the air were these teeny tiny 1 centimeter lichens that held the soil together. But as a use of drones, if you stepped on these lichens, they would die and take about 500 years to grow back properly and stabilize the soil. So drone surveying for them was really fun. Welcome to this little class within a class. This is module 1 of 3. The goal of all of these modules is to show you how you can take drone data, which is normally photography, and feed it into a precision application tractor as a classified shapefile. And I'll show you what that means as we go along in the lesson. We'll actually address it at the end of the lesson. This module will give you a bit of the background on the history and uses of drones in general before we get into agriculture. So the objectives of this module is to teach you about aerial photography, its development and use, radio-controlled aircraft and how they developed into modern drones, the sensors that are used in drones and what they are used for, a brief introduction on the art and science, the whole field of remote sensing. And finally, we'll go over a research paper to show like what kind of questions you can ask with drones in agriculture. First, let's talk about the history of aerial photography. The first aerial photos were taken in Paris, France in 1958 via hot air balloon. They were unfortunately mostly lost to time, but the earliest surviving hot air balloon photo is this one, which is Boston as the eagles and wild geese see it. Now, this type of photography was mainly used as art and tourist novelties at the time. However, eventually the balloons became more stable and used in new applications, such as blimps, which were used as reconnaissance as well as for lifting instruments in the air, such as barometers, but notably not very many photos, maybe for land surveying, but not for reconnaissance. The advent of kites eventually led to the fixed wing aircraft. The Wright brothers utilized them in their designs. So this was 1906, and in 1912, they were used in the First World War, but they did not have many many cameras attached to them at that point because they were too low quality and took too long to develop. So they actually had cartographers flying along with the pilots to draw maps to hand to generals. However, the French eventually got the process of developing the photos down like clockwork, and the use of photography in planes was widely adopted later in the war. Speaking of clockwork, with the miniaturization of cameras and timers and film, pigeons were also used in World War I and were equipped with little cameras attached to their chest for reconnaissance missions. I kind of like to think that they're the first drones. With photography becoming a larger part of reconnaissance, faster planes with better cameras were used at higher altitudes. Eventually, sensors on satellites were placed into space to remotely sense the entirety of the Earth. From the 1970s, better sensors that can scan at higher resolutions more frequently have been consistently developed and placed into space. However, even the best of modern satellites still produce images that are broad swaths of the landscape that only come by every once in a few days. And they just can't answer small scale questions, such as which plants are struggling in my field. So, with satellite photos being too coarse, aerial photography remained the best tool for land surveying. And in fact, aerial photo interpretation was taught in the geography department here at NMSU until 2017. Old aerial photos are some of the best documents for historic land use, and the art of interpreting them is still useful today. These types of photos were taken in stereo to gain a depth of field. The interpretations often involve documenting hills and slopes, and so interpreters use these stereoscopes to view the photographs to gain a depth of field. This was such a widespread technique and generally used that the National Cooperative Soil Survey wrote into their protocols how to interpret aerial photography into the soil survey itself. So if you ever run into a soil map, it probably is based off of aerial photo interpretation. Now on to radio controlled aircraft. We already talked a bit about kites and their use in aerial photography, but let's see how they evolved into radio controlled aircrafts. The first box kite was invented in the 1890s in Australia, which aided in the design of the modern airplane. The original airplanes utilized kites in their design, which were controlled by tethers. This was eventually brought into the toy tethered plane, which you can still buy and fly at the local RC airport in town. There's a special field for tethered aircraft to spin around, and it looks a bit like this. From there, radio controls started to be used in airplanes in the 1930s, the invention of which is credited to Walter Good, seen here. Much like the cameras attached to pigeons, radio-controlled powered aircrafts was possible in part by the miniaturization of engines and motors. Both gas and electric-powered aircraft are found modernly, with gas-powered being more maintenance-heavy but being able to fly longer with heavier loads and better turnaround time if you needed to keep surveying all day. Electric motors are the most common in RC aircraft due to its low maintenance. Don't need to change the oil on an electric motor, and the availability of modern cheap electric parts. Eventually, they were packaged into ready-to-fly kits. The invention of radio controls for aircrafts wasn't just for toys and hobbyists. The first prototype of a helicopter, seen here, was built in 1941, which utilized radio control for safety. This was in the Bell Labs, which went on to build helicopters for military applications. Bell also patented one of the first three-dimensional kites and wrote about them in National Geographic in 1903, which one of the original copies we can find in the Zool Library. From those original helicopters, the helicopter itself was rather dangerous, and Bell Labs found that adding multiple rotors to the machines gave more lift and stability. Thus, the first quadcopters were born. However, due to their complex nature of construction, the Army the Army preferred the mass producible single rotor system. With how popular RC helicopters are becoming, prices are becoming cheaper to the point where you can go to any big box store and pick up one RC helicopter for $20 instead of a couple hundred. This meant that there's a lot more supply on the market for companies to tinker with the parts on RC helicopters. Since these little since these were rather unstable, using just the one rotor, multiple rotors were again introduced to these helicopters for stability and to lift more weight with small motors. From there, the next logical step is to put a camera on a quadcopter. And so the quadcopter revolution took off. Now we can get on to the evolution of quadcopters. For example, we'll use the DJI Phantom line, but there's tons of others, and the DJI just shows a really clear evolution. With the release of Phantom 1 here, we have a working design of a quadcopter with kind of a GoPro-like camera dangling from below. It's not controlled in any way. It's just a timer like on the Pigeons. The Phantom 2 improved upon this design by stabilizing the camera with a gimbal, and it communicates to the drone, and then the drone communicates to your phone with an app that you can view through the camera. The Phantom 3 changed the thought process behind drones. This went from a toy to a survey instrument, and it did this by changing the control chip. While there isn't much of an outward change of appearance, the brains of this RC helicopter are much more advanced. This drone has GPS in it, which talks to the flight controller, and the control software can tell the drone exactly where it is and the inputs of the air and how it's moving so that it can be stabilized. And this can also be controlled by an app to plan where it's going to fly. This is what I would say, where I would say an RC helicopter becomes a drone, as it has the ability to fly autonomously. Finally, like in the evolution line, is the Phantom 4, which has an even better camera, stability system, vibration dampening, and better control software. This is what I use in the field, and I haven't really found a reason to upgrade to any of the newer systems yet. This drone can fly a survey a couple of acres and get a resolution down to a square centimeter and even below that. And it can do this all in about a 15-minute survey. It's really cool. So I want to show you the difference between a drone and a RC helicopter in terms of stability. So on the left here, we can see the $20 big box store RC helicopter taking off, and this is just me pressing up on the control stick. It doesn't have any GPS or controller in it, and it just kind of takes off with a gentle breeze. Now, the Phantom that you're seeing on the right is my surveying drone. It does move just a little bit in the breeze, but have my hands off of the controller. It's just staying there very stably without me telling it to do anything. It's a cool little toy. These electric quadcopters come in a few sizes based on your needs. The Phantoms are the workhorses of the agricultural surveying industry, as they can lift one of the tiny cameras that are commonly used in the surveying. Much of the larger 6-rotored copters have a wingspan of about 6 feet and can lift 15 to 20 pounds rather than a couple of ounces. These are what are used for modern movies and TV shows instead of cherry pickers. However, we actually have one of these in my lab to lift a heavy hyperspectral camera, such as the one that we were seeing in my introduction. The smallest ones DJI offers are below 250 grams, which avoids the FAA regulations requiring them to be registered or using a Part 107 license. This allows people to use them recreationally, like for Instagram and for YouTube. Which one of these drones you get, it depends on your use case. Now we get on to the science part. What type of sensors can we put on our drones? A sensor is anything that can detect information from the surrounding environment. The most common one on a drone is a simple camera. This sensor detects photons that are red, green, and blue in wavelength. The red, green, and blue are collected separately in what is known as bands. A multispectral camera is any camera with additional bands, additional band or two. The most common in agriculture is infrared and near infrared. A hyperspectral camera is a sensor that has hundreds of bands. This is used for spectroscopy and can help determine the specifics of an object, such as differentiating between different plant species. And I'll talk more about their use in a minute. Thermal cameras can also be mounted on drones and are commonly used for insulation surveys on buildings. LiDAR sensors can be mounted to drones. This is an active sensor that produces a laser and then waits for the light to bounce back. The speed of light being known, this sensor can determine the distance and topography of the ground down to a few millimeters. This also has the benefit of being able to see through vegetation, as the laser will eventually find a gap through the leaves and hit the ground and then bounce back. Other weirder sensors include ground penetration radar, which can be used for measuring lakes, snow level, and the shape of bodies of water. And there are even weirder sensors, such as gravity sensors, that detect dense, heavy ore deposits from the air for mining. So that's enough about sensors. You'll eventually figure out which one you need for your own application. But to better educate you on which sensor you should choose, we're going to cover a bit about remote sensing itself. And to start, we'll start with the light theory. So light is made up of photons. These photons are particles which move in waves. These waves have peaks and valleys, and the distance between these peaks and valleys is known as the wavelength. The more energy that's in these waves, the shorter the distance in between the peaks become, thus shortening the wavelength. So lower wavelengths have higher energies. Wavelengths can be any distance, and so this is known as the electromagnetic spectrum. Our eyes can detect a small slice of the spectrum from about 400 nanometers to 800 nanometers. This is seen on this blown out spectrum from radio waves, and then the visible light spectrum being just this very tiny sliver. Most passive sensors detect photons. Each band is a small bucket on the spectrum. Each one of the lenses here on this multispectral camera is one band, one bucket for red, green, and blue. Next, these extra lenses detect near infrared and infrared. This is known as the red edge, a phenomenon that happens with chlorophyll. And I'll show you a bit about it in a second. This is a really common spectrum. This shows how much light is being reflected from a leaf. Chlorophyll absorbs visible light to make food for the plant. So you can notice that the x-axis here is from 0.4 to 0.8 is the visible light spectrum. It's just in micrometers rather than nanometers. Red and slightly into the infrared helps plants produce the most amount of food, and so it's absorbed the highest. but lower wavelengths into the infrared start to damage the plant, giving them a sunburn. So plants naturally reflect this. To do this, cells called spongy mesophyll inflate with water to reflect the infrared. The more water in the spongy tissue, the more the light can be reflected. This is kind of taken to mean that the plant is healthy. Now, where these measurements get helpful is if we want to take an area and know if a crop is growing or if there's bare spots in the soil. Here we can see a spectrum of soil overlaid on the leaf reflected spectrum. Soil has a higher reflectance of red, brown is a type of red, and a lower reflectance in infrared. If a spot has low reflectance in red and high reflectance in green, then we can be confident that it's not soil. Now, water's on here too. It reflects slightly in the visible light and peaks in blue, but absorbs almost all infrared light. So for low red and low infrared, we would expect water. For high red and low infrared, that's soil. And for low red, high infrared, we would expect to see leaves. And if we're reflecting just about everything, then we have kind of a mirrored surface. And we just are interested in things that have low red and high infrared reflectance. The plant gets water stressed, the spongy mesophyll starts to deflate and stops reflecting infrared. The chlorophyll in the plant also requires some water to actually make food, and so doesn't need all of those red photons, so it starts to reflect them. This is an unhappy plant. The spectrum from this starts to look similar to soil. If we took a ratio of red to infrared, we could get an indicator of a plant's health. In reality, this just measures how much spongy mesophyll and chlorophyll is in an area, but don't really tell that to plant people. I'm a remote sensing guy. In a final note about spectrums, each plant has a unique spectrum, and scientists catalog the spectrum into libraries. Here we can see that grass reflects more infrared than a walnut tree. If you had enough bands, such as a hyperspectral photography sensor, you can determine which plants are which just based off of their spectrums. All of this can be done on a drone. To tie everything together, let's answer a question with drones. So here's a paper I found that asked a simple question. In a potato field, potato beetles are a problem that we need to detect fast, like today. Can we detect them using a drone? So we have a potato field and a drone. How do we detect these beetles? Well, there are holes in the spongy mesophyll, meaning that it can't reflect infrared as well or absorb green very well. They use the same camera that I mentioned with the multispectral one and used a very common index, a ratio, which is known as the normalized differential vegetation index. And nobody likes pronouncing that, so they just say NDVI. This means the ratio between the difference of infrared and red, and the difference between the maximum values of infrared and the maximum values of red for that given survey. This value is uncalibrated and is only valid within the area that you are measuring during that single measurement period. It's not perfect, but it gives you quick and general idea of what's happening in your crop. The researchers imaged the potato field and then released beetles into the field. They came back the next day to see if they could detect the damage by the beetles. Here. The output that the created was this classified map. And if you ignore the edges of the field, you can target just those areas to apply pesticides. And you can also skip fields that don't have any beetles in them at all. This classified output is called a shapefile and can be directly fed into a precision variable rate sprayer and can be used to kill the beetles. That's just one way that we can use drones in agriculture. Hopefully, you can come up with some novel way to use drones in your own research. In closing, we covered the history of aerial photography from balloon to satellite, how kites and RC aircraft are interlinked, and how RC aircraft developed into modern drones. We discussed the types of sensors that are used with drones and some of their uses in agriculture. We discussed the theory of remote sensing, the electromagnetic spectrum, reflectance of spongy mesophyll, and how to calculate NDVI. Finally, we briefly looked at a paper about how we can use drones in agriculture to detect pests and apply pesticides using a classified shapefile. With the rest of the modules, I'm going to teach you how to collect the data and how to process it into that shapefile so that if you ever run into one of these precision tractors, you can feed something into it. The next module will be about how to actually fly the drone in the field and take survey data. But that's the end of this module. So if you have any questions, feel free to get in contact with me or Dr. Edgar, and I'll hopefully be able to answer them. This semester, I'm just writing my dissertation, and I long for any excuse to not write it. So feel free to bother me with any questions that you have about drones. So I'll see you in the next module.